Okay, so when we get to where we're comparing two means, where we have two different populations, each population has its own mean, and we have the same problems as before that we typically don't know the population means, and also typically don't know the population standard deviations, although when we start out, we're going to assume that we do know them to make things just a little simpler. What we really might be interested in knowing is whether, say, the two means are equal, or maybe whether the mean for population one is less than the mean for population two, or maybe whether the mean for population one is greater than the mean for population two. And there are a lot of scenarios where you could be interested in comparing two means on the basis of some samples. But I think the one that's kind of most common to think about is, say, a drug trial of some sort. So let's say we have some new pharmaceutical treatment that we think is effective. We set up an experimental group with some folks in it, and the control group with some other folks in it, right? Maybe these folks all have the same disease, they all have the flu or something, and we're going to give them a treatment, give a treatment to the experimental group, not give that treatment to the control group. And then we want to know if, say, maybe the mean time to recovery or something like that, or the mean cost for treating this person, or whatever it may be that we're interested in, is different from the control group, or maybe do we want to know if the mean time to recovery is lower for the experimental group that got the drug than for the control group that didn't get the drug, something like that. So we have these two groups, maybe group one and group two. These would be from hypothetical populations of people who had this illness and were treated versus people who had this illness and were not treated. So even though these two populations don't, in a sense, exist right now, like even if I had unlimited resources, I couldn't go out and get all of the people who have been treated and all the ones who haven't been treated, because the treatment doesn't really exist in the population yet. We're really actually, in a sense, looking forward in time and saying, okay, hypothetically, if we went down this branch where we offered this treatment to a bunch of people in the population versus this branch if we didn't, how would those two timelines diverge? So this is another way that we're stuck with samples instead of populations, because we can't go forward in time down this pathway, then reversing it on the other pathway and see which one was better. And this first sample has characteristics x bar 1, S1, and N1 for the sample mean, the sample standard deviation, and the number of individuals in the sample, and then similarly for sample 2. Okay. And we had mentioned before that really the reason that the normal distribution pops up in the central limit theorem is that it has this kind of stability, that if we take averages of normal distributions, or sums of normal distributions, or therefore differences of normal distributions, we get a normal back. So the difference of normal distributions, x bar 1 minus x bar 2, is normal. Its mean is the difference between the two population means from 1 and 2. And its standard deviation is given by this kind of relationship here. In other words, the variance of the difference is the sum of the variances, right? The variance of x bar 1 is this standard error, sigma 1 squared over n1, and the variance of x bar 2 is sigma 2 squared over n2. And as I mentioned before, variances kind of work out nicely mathematically quite often. So in this case, the variances just add. And standard deviations often are a little more annoying to deal with mathematically, but they have nice units, so they're nice to report. So we see that the variances just add. We can develop a confidence interval for the difference between the two means, mu1 minus mu2. This difference between the two means is what we're going to call mu. Mu will be the difference between the means. And it's given by lower to upper is point estimate, So x bar 1 minus x bar 2. And here I'm not being super careful to write observed or not, because, so for instance, up here, when I say x bar 1 minus x bar 2, I'm talking about the random variables. And down here, I'm talking about the actual observed quantities from the samples. I think at this point, we kind of have a feel for when we're talking about one versus the other. And we already have lots of subscripts running around. So I think throwing in an observed on top of that is a little unnecessary, and just makes it really difficult to read. So these would be the observed x bar 1 minus x bar 2. Or in other words, this is the point estimate for mu, our best guess for mu, plus or minus a z number. So this would be like z alpha over 2 for a two-tailed confidence interval, times the standard error, times sigma for that random variable, which is the square root of the sum of the variances, square root of the sigma 1 squared over n1 plus sigma 2 squared over n2. So again, same form, point estimate plus or minus some number of standard errors. This should look very familiar from our work in confidence intervals. And all that we need to do is just replace our point estimate and our standard error with the ones for this distribution. One note that I wanted to say and forgot to say on confidence intervals, I posted a supplement on bootstrapping for confidence intervals and pushed the due date. I don't remember what the due dates were in this course originally, but I pushed all the due dates back to 12/10 for that section 7.4 in bootstrapping. So if any, I had some people that had questions, mainly that reached out this past week. So I just kind of posted that supplement and reopened that for everybody. So if you want to take a look at that supplement, that might help a little bit with bootstrapping, both with the understanding the background, which I think we kind of covered pretty well in class, but also the techniques of entering everything into Excel and so on. But okay, so sorry for that digression. We also might be interested in a hypothesis test for the difference between the means. In other words, maybe I'm interested in time to recovery for my experimental group that took my drug versus the control group that did not. And what if I have a time to recovery of, I don't know, let's say 28 hours versus 36 hours. Okay, my sample mean, x bar 1 observed or x bar 2 observed. Well, my sample mean time to recovery for the experimental group is less than the control group. But then the question is, was this just due to chance? Was this just due to sampling error? Maybe I just happened to put a few extra people in my experimental group who would have gotten better quicker anyway. And maybe I put a few extra people in my control group that would have taken a little bit longer anyway. And just by chance, that's how it worked out, even though my medication doesn't actually do anything. Or is this a big enough gap where I can say, well, for a gap like this of, let's say, 8 hours to have existed in this type of a sample, in this type of a setting, that would be so unlikely to happen if the means were actually the same, that I would prefer to reject the null hypothesis, the means are the same, and go with the alternative that mu1 is actually less than mu2, and that my medication actually does have some effect. So that's what my hypothesis test might look like, is the natural way to set it up would be something like this. Hypothesis test, or H naught mu1 equals mu2, and H1 mu1 is not equal to mu2. Or over here, I might, instead of not equal to, I might have mu1 less than mu2 that I might be looking to show in a scenario like this. Testing that against mu1 equals mu2, which kind of encapsulates all of the mu1s bigger than or equal to mu2. I have a little bit of a problem here, though, more of a practical problem. what's the first thing that I want to do here? I want to assume H naught is true. So I want to assume that mu1 equals mu2. But I don't know mu1 or mu2. So I want to do something like, say, assume H naught is true, draw a normal distribution, and stick the center at some particular number so that I can compute the p-value or the rejection region or something like that on the basis of this center. But I don't know what that center is, right? Because I just have mu1 equals mu2. So it turns out that the way that we want to set up our hypothesis tests is to just make one small change. We introduce a new variable called mu, which is mu1 minus mu2. Note that if we had access to both populations, their mu1 and mu2 would be fixed numbers that we don't know. We could subtract those numbers in theory, and that would yield a third fixed number, mu, which is also a fixed quantity, but that we don't know. So we can say a similar thing about mu, that it is a fixed quantity that we don't know. But mu1 minus mu2 under the null is 0. And now, if I assume H naught is true, I can stick this middle point, this center of the distribution, at 0. And that gives me something tangible to work off of. So when I run these hypothesis tests for difference between two means, I'm testing for mu, the difference between the two means. And then, of course, my point estimate is something like x bar 1 minus x bar 2. My standard error is going to look like this. And I basically have the same setup that I had back when I was just testing for one mean when sigma was known. This is essentially the same setup, right? I have a mean that I'm interested in knowing whether it's 0 or maybe not 0 or less than 0, bigger than 0. I have a point estimate for that mean. This number, x bar 1 observed minus x bar 2 observed. So it'd be, I suppose in this case, it would be -8 would be my x bar observed. My hypotheses are mu equals 0 or mu less than 0 in this case over here. And then I have a certain standard error that's based on sigma 1 and sigma 2 that's, a little more complicated to compute, but it's just going to be some number when we plug all that in our calculator. And we can do things like, say, compute a test statistic. Of course, our null hypothesized mu1 minus mu2 is 0. So that little bit goes away, and I end up with just the numerator of x bar 1 minus x bar 2 and a denominator of the standard error. The denominator looks a little messier than it did before, but it's not, it looks messy now, but if you just compute this is a number, plug that number in here. If you do this computation outside of the fraction, it's just the number that you're going to be dividing x bar 1 minus x bar 2 by. So it looks messy. It's not that bad, though. And then the question is, well, what if we want to generalize this a little bit? And what if we, so up here, I assumed that sigma was known. What if I instead want to evaluate the case where sigma is unknown, probably a more realistic case? Well, then what do? Well, we basically just do the exact same process. I mean, these sigmas would turn into s's. We'd use our t distribution instead of a z distribution. So this test statistic or these p-values or this this index up here on the confidence interval, those would be gotten off of the t distribution table instead of the z table. we need to use degrees of, or we need to know degrees of freedom to use T. And the degrees of freedom calculations are a bit complicated. So there is kind of a longer degrees of freedom calculation you can do to give kind of a more precise degrees of freedom. But a pretty good, let's say something like a conservative approach is to take degrees of freedom as the minimum of n1 minus 1 and n2 minus 1. So I take my first sample size minus 1. That gives me a number. Maybe that number is like 30 minus 1 is 20. Maybe there's 30 people in my experimental group. And 2 minus 1 for my second sample, maybe there's 50 people in the control group, so that's 49. So I look at 29 versus 49, and I say, which one of those is smaller? Remember, smaller degrees of freedom means that the T distribution is like heavier tailed. So we're paying a little more of a penalty for using T. We're paying a little more of a penalty for not knowing both of these standard deviations. So basically what we're saying is the penalty that I pay for not knowing either standard deviation, I just kind of take as the penalty that I pay for the worst of the two. So if I had, say 29 here and 49 there, I just go with 29. I would just, take that kind of whole penalty of the first sample being smaller and just go with that. Again, you can, there are some calculations you can do that that will give you a more accurate degrees of freedom, but this is a good approximation though. Okay, so in practice, what does this look like? So here we have heights of 9-year-old kids. We want to construct a 99% confidence interval from the mean difference in heights between boys and girls. And at the 5% level of significance, can we conclude that girls are taller than boys at this age? So let's suppose that mu1 is related to girls, and mu2 is the mean height for boys at this age. And I set this up so that when I do mu1 minus mu2, girls minus boys, if I think the girls are taller than boys, then that's going to be a positive number. So I just set this up to kind of avoid negatives. If you set it up the other way, it's not a big deal. It's just you'll have some negative numbers floating around. But when I can, I try to avoid negatives. It's sometimes just easy to miss a sign or make a mistake. It's easier to make a mistake if you have more negatives floating around. Okay, so mu, the variable of interest, is mu1 minus mu2. So mu is like girls minus boys. I'm just making notes up here so that I keep myself straight on which order I'm doing things in. My point estimate for mu x bar is x bar 1 minus x bar 2, or I'll kind of rename that x bar girls minus x bar boys. And I see that that is 126.2 minus 123.5. And that's what? So that's 3 minus 0.3, 2.7. Yeah, looks good. So this is my, what I might call like x bar observed. I need to know my standard error, sigma. This is for this variable, the difference. And again, remember that was the square root of the sum of the two standard errors. So sigma 1 squared over n1 plus sigma 2 squared over n2. Be a little careful, even though we're subtracting the variables, we're adding the variances, right? If we just have more things in play, whether we're adding or subtracting them, there's just more variation that can happen. So this is going to be sigma. It doesn't if I got the ones and twos backwards here, it wouldn't matter, but I'm going to, work to keep everything consistent, even when it wouldn't matter according to the math. So the girls are 1. So sigma 1 is 120. 120 squared over N1 is 50. It is important that the 120 goes with the 50 and the 98 goes with the 60. Oh, made a little mistake there. 120 is sigma squared, so we don't want to square it again. It's just 120. And then sigma squared for the boys is 98 over the sample size for the boys is 60. And let me jump over to the calculator for that. I will switch my screen share here. Okay. And what do we need? We need the square root of 120 over 50 plus 98 over 60. Does that look right? Looks good. The division will be done before the plus, so that's not a problem. We've got our parentheses all done. And that gives me almost exactly 2. I'm just going to put equals 2. And that is our standard deviation. And at this point, we can say, okay, we want a confidence interval. So what's our 99% confidence interval for mu, the difference between the means in this direction? So if mu were positive, the girls are taller than the boys and vice versa. Well, that's going to be my point estimate, 2.7, plus or minus an index. But since I know sigma, this is going to be a z index times my standard error. But my standard error I just calculated was 2. Okay. I've got a bunch of junk on my desktop because I was doing a bunch of stuff this morning, but so ignore the mess on my desktop. I want a 99% confidence interval. That tells me 99% in the middle, 1% between the two tails, 0.5% in each tail. So I want to know the 99.5 percentile of z. So I'm looking for 0.995, and I see that's one of these like special cases, 2.575. I could alternatively go to my t-table, look up two-tail area of 1%, but I don't want t, I want z. But remember, if we go all the way to the bottom, that gives us z, 2.576. So we'll just say 2.58 for our z number. And we go back to our calculator, 2.7 plus 2.58 times 2 gives me 7.86. That was the upper bound. And then the same thing. I don't think I actually saved any keystrokes there, but negative 2.46 for the lower bound. So there's my 99% confidence interval for the mean, for the difference between the two means. Or in other words, I'm 99% confident that this interval from negative 2.4 to positive 7.9 covers the true mean mu. Now, something that I note is that 0, mu equals 0, or mu for girls equals mu for boys, that they really have the same population mean, that is within this interval. 0 is between negative 2 and positive 7. So So according to this confidence interval at the 99% level of confidence, it seems plausible that the true mean for the boys and the girls could be the same. So at this point, we've like almost done a hypothesis test, but we have two details. Number one, we actually want to do all the details just to be careful. And number two, note that the level of significance is different for the hypothesis test. This is just due to the problem statement. There's not a particular reason for that, but just to see a couple different numbers being used. Okay, so we want to test at the 5% level whether girls are taller than boys. This is also a very important detail, is that we're only testing in one direction. In other words, my alternative if we're testing whether girls are taller than boys, that means mu bigger than 0. This is what we chose to test, right? We shouldn't decide to test in this direction after we see the sample and we see, oh, X bar for girls is bigger than X bar for boys. So now I'm going to decide to do one-sided instead of two-sided or something. But maybe we decided this in advance. We said, hey, somebody told me somewhere that girls are taller than boys at this age, and I don't know if that's true. So I'm going to develop a test to try to determine whether that's true. So we're going to say the alternative is that mu is bigger than 0. In other words, that mu for girls is bigger than mu for boys, right? Mu for girls minus mu for boys is bigger than 0. So that's what this means. And my null is that mu equals 0, which remember encapsulates all of the mu's less than or equal to 0. So I can't use this confidence interval to directly answer my question for a couple reasons. Again, number one, I really want to just go through all the formality of the hypothesis test, just make sure I have all the logic right. Number two, it's at a different confidence or a different level of significance, 1 versus 5. And number three, this hypothesis test is one-sided, but my confidence interval is two-tailed. So really, for all of those reasons, I can't just look at the confidence interval and say, yep, 0 is in there, I'm done. Okay, so again, what do I have? Well, let's first assume H naught is true. Then the distribution of X bar is centered at mu, which is 0. We have X bar observed. What is X bar observed? That was 2.7. We calculated that above. That doesn't change. So here is X bar observed 2.7. I note that this is a right tail test. So X bar observes that are very high, very far to the right would be good evidence to reject H naught in favor of H1. But X bar observes that were far to the left would be very poor evidence to generate a rejection. So if I rejected for 2.7, I'd also reject for 2.8 or 3.0, anywhere further to the right that would represent more evidence. I can calculate my p-value. So this is the probability that what? The random variable X bar is bigger than 2.7. Or this is the probability that, well, Z is bigger than the standardized value, 2.7, minus the null hypothesized value of mu, but that's always 0. I don't really have to write it in there. We kind of omitted it in this Z critical formula up here because it's always 0 that we're testing against, but I'll put it here explicitly just so we see where everything comes from, and divided by the standard error for X bar 1 minus X bar 2, which was 2. And what's 2.7 over 2? I guess that's 1.35. Don't really need the calculator for that. Probability Z bigger than 1.35. Well, I could say that that's probability Z is less than, flipping over 0. So the right tail becomes a left tail, and the 1.35 becomes a negative 1.35. So using that symmetry. And I need Z. Where's my Z table? Probability Z less than negative 1.35. So here's my 1.3 row, 0, 1, 2, 3, 4, 5. So there's my 0.05 column. This is 8.85%. And that's my p-value. That would be, if I rejected on the basis of this sample, that's the experienced probability of a type 1 error. Remember, our level of significance is our maximum allowable type 1 error. So I'd say since the p-value is 8.85%, the experienced type 1 error rate would be almost 9%. That's bigger than 5% alpha, our maximum allowable type 1 error rate. So if we chose to reject H naught, we'd make an error 9% of the time, but we're only allowed to make it up to 5% of the time. Do not reject H naught, or on the basis of this sample, we cannot conclude that at this age, girls' mean height is greater than boys' mean height. Or in other words, this sample difference, this difference between the sample means, it could well have occurred just by chance, just by sampling error. Are there any questions on this? So in this fairly simple setup, the details look a little bit complicated, but I think that we hopefully saw that this really isn't any more complicated than doing a z-test for mu when sigma is known for a single mean. After we get past the details of setting up which sample is going to be sample 1 and which is going to be 2 and maintain that consistency, and then compute our point estimates, x bar observed, or our point estimate x bar observed, as well as our standard error sigma. Once we do these computations, this setup here, everything that I wrote below this line, if you just looked at this, you wouldn't know whether this was testing for a difference between two means or whether this was just testing for a single mean, just like we did in chapter 8. Now, something that I kind of glossed over before is the assumptions. And the assumption, or the important part of the assumption, the new part, is that we have two independent samples. So for instance, we have an experimental control group where I take, let's say, 100 people, I randomly sort them into experimental versus control, and I give the experimental group a drug, the control group no drug, and I follow them from whatever, a week or something, and see how long it takes them to recover from being sick. If I were instead, let's say, studying weight loss or something, and I, if instead of like this, if I had, population 1, so to speak, was, these 100 people's weights at the beginning of some exercise program, and then, quote, population 2 was those same people's weights, a month later after they've gone through some exercise program. Well, now there's not independence, right? In other words, if Bill Smith is, heavier than average at the beginning of the program, he's probably going to be heavier than average at the end of the program, because Bill Smith is in sample 1 and sample 2. And so is, Susie Adams, and so is, each other person. It's the same people in these two samples, so they're not independent samples. So in that case, I would, more likely choose a different technique to use. But again, we're not getting into those difficulties. If I wanted to take something like that, take a situation like that and set it up to be simple, random independent samples, what I might do is, offer this program to 1,000 people, randomly choose, 100 to be the ones who I test their weight before the program starts, and then another 100 to test their weight after the program ends, or something like that. But usually if I have the choice between the two, between setting up the experiment in a way that forces independence like that, or being able to use an inherent pairedness, I'm probably going to go for the pairedness, right? That's probably going to be the better setup. But again, we're kind of taking the simplified approach here. So probably the better setup overall would be to use the paired setup, but the math is simpler this way. So we're certainly not making an attempt to do an exhaustive treatment of something like testing for the difference between two means. Okay, and then let's do one more problem just fairly quickly. So we have some data on the driving speed of male versus female drivers. And can we conclude at the 10% level that there is a difference in the mean driving speed of males versus females? So a difference could be if the males drove a lot faster than the females, or if the males drove a lot slower than the females. So let me set up, I want mu1 minus mu2. Well, the males in the sample seem to drive faster than the females, so I'll set this up as males minus females. That way I'm mostly dealing with positive numbers. Note an important distinction here is I do not want to decide on this word on the basis of my sample. I don't want to look at my sample and then say, oh, well, what I really meant to say was, can I conclude that males drive faster than females? Because I look at my sample and I see that X bar for males is bigger than X bar for females. I don't want to do that. I don't want to change the nature of my test on the basis of my sample, but just changing which sample or which population I call population 1 versus 2, that doesn't really change anything, right? It's just a labeling issue. So I'm just going to label them in the way that's more convenient for me. So deciding to use mu as males minus females instead of females minus males, that doesn't really change the nature of the test or the experiment that we're running, anything like that. It's just labeling them so that it's easier for me to work with. Okay, so my hypotheses, H1 is that mu is non-zero, in other words, that there is a difference. H0 is that mu is equal to 0, that there's no difference in the means. X bar observed is X bar for the males minus X bar for the females. So that's 2. And as always, let's assume that H0 is true. If H0 is true, then mu is 0. So X bar, the random variable X bar, which would be X bar 1 minus X bar 2, or X bar for the males minus X bar for the females, that's centered at 0. And this time, just to review, let's do rejection region. So this is a two-tailed test. If I was computing a p-value, I'd have to make sure to take whatever area I'm looking at and multiply it by 2. If I'm looking for a rejection region, I need to use a two-sided rejection region with a lower and an upper bound. And this is going to look a lot like a confidence interval, but remember the detail that we're centering at 0, not centering at X bar observed. So this is going to be 0 plus or minus some Z number that we'll find in a second here, times the standard error. So we also need to know, maybe I'll do that up here. We also need to know sigma. So what is sigma? It's the square root of the sum of the individual standard errors. And I'm going to try to respect the 1 minus 2 males before females and all of these so that we have consistency, even though it wouldn't be a big deal if you got them backwards. So 2.2, here we're given sigma, so we need to square that over 27, and 2.5 squared over 18. So I have square root 2.2 squared over 27 plus 2.5 squared over 18. And okay, that looks good. And this gives me about 0.73. So what is my quote confidence interval? What is my rejection region? What are my rejection region bounds going to look like? The middle of the distribution, 0, plus or minus some z index we'll find in a second, times 0.73. We need a z index for a two-tail test. I can't select it. There we go. At the 10% level. So I have 5% in each tail, which means I'm looking for the 95th percentile of z, right? 5% in the right tail means 95% to the left. So I'm looking for the 95th percentile. I see that z index is 1.645. I could also get it off the t-table like I showed you before. And here I do 1.645. Oh, not sure where I was typing there, but 1.645 times 0.73. And this gives me 1.2 pretty much on the nose. So this is 1.2 on the right, negative 1.2 on the left. So I can say if X bar observed is less than negative 1.2 or bigger than positive 1.2, we reject H naught, otherwise do not reject. And then lastly, we can say since X bar observed equals 2, which is indeed in this right tail, this right side of the rejection region, which is greater than 1.2, reject H naught in favor of H1. And we can conclude that mu for the males is greater than mu for the females on the basis of this sample. Now this brings up an idea that we'll talk about in the upcoming presentation. What does the effect size seem to be? Not very large, right? Or if I was going to make a confidence interval for the difference between the two means, it would be something like from 0.8 up to like 3.2. Does driving like 2 miles an hour faster, is that an effect that we're likely to care about in what we're studying? Probably not. So you can have something that's statistically significant, but not practically relevant. So that's also an important note here. Also note that, the observed difference of 2 units here versus the observed difference of 2.7 units here, one was significant, one was not, and that has to do with things like the standard deviation and variance and so on, and the sample size, and right. So there's a lot that factors into whether something is statistically significant or not that's beyond that effect size. The effect size is obviously important. If the effect size was 0 in the samples, we certainly wouldn't get significance. but there's more that goes into it than just that effect size. Okay. So again, this is something I could talk about for quite a while. But I'm going to try to go fairly quickly and really hit the high points here. So one of the downsides of hypothesis testing and really frequentist statistics in general is that the interpretation can often be challenging. So when you do all the calculations and you're like, okay, great, I got this thing, I got a result that says this is my confidence interval, I got a result that says yes, reject H naught in favor of H1, and your p-value is 1%. Like, great, I got those numbers, but now somebody's asked me, what does that mean? Right? How should that affect my life or my worldview? Or so I have to give an interpretation. And a lot of times that's a pitfall. And there are some others as well. So that's really what this is about. This is about saying, okay, we learned these inferential statistics, we learned these methods, we can do the calculations, but just reporting a number or a confidence interval or p-value or a hypothesis test result, reject or don't reject, that's all well and good. But when somebody asks the question, why did you do what you did and what does that mean, we can get into a sticky situation there. So, okay, let's take a look at some just kind of various issues that crop up. I think the first one is something like problems with alpha, our statistical significance level. So why do we use alpha? I mean, alpha of 5% is like almost set in stone. I've mentioned a couple of fields where maybe they use 10 and 1% fairly often, but even the fields that use 10 and 1%, they typically report 10, 5, and 1%. They typically don't like ignore 5 and just report the result for a 10% level of significance. So why 5%? Why not some other percent like 1 or 10%? Or for that matter, I mean, you might have looked at this and said, it's kind of strange that we pick nice round numbers that to humans look nice, but why not 12%? Why not pi squared over 4%? It seems somewhat arbitrary that we picked 5%, and that's just what we use most of the time. And you can read the details here, but as far as I have been able to tell, basically the reason that everybody uses 5% is because a statistician who roughly 100 years ago was extremely influential in frequentist statistics and developing it and really getting these methods out there for researchers to actually use. In his book, he essentially says, okay, well, because this isn't 2023, this is 1923 or 1925, you can't just use whatever significance level you want and type it into Excel and have it tell you what the p-value is or whatever. It's much more of a hassle to do any kind of calculations like that. So we'll pick p equals 0.05 because that gives me a z critical of basically 2. So we consider 2 standard deviation or 2 standard error deviations to be significant. He's writing this in a textbook, so he's basically just saying we're going to pick z critical equals 2 or the critical number equals 2 for this book. But I don't think, I think if you read on, I don't think that he's saying that research workers everywhere should always use z critical of 2 or an alpha of 5% for their tests. I don't think that's the point that he was trying to make. I think he's saying that this isn't an absurd number to pick. It's not like you're picking a 40% value for the significance level. So you won't have to follow up on negative results. You won't have to do extra work for fruitless for no gain very often. But also 2 is just a nice convenient number. It kind of it's kind of at the intersection of 2 nice numbers for humans, 5% versus z equals 2. So and a practical reason why people use alpha equals 5% is Everybody uses it because everybody uses it, right? There's a status quo bias. And to be fair, there's something to be said for that, in favor of that, that if we have 40, 50 years of medical literature all using alpha 5%, and then, you know, starting this year, we decide to use alpha equals 8% for some reason, well, that makes it very hard to compare new results with old results. You know, certainly not impossible, but it makes the comparison a good bit harder. Also, the power in medical literature tends to be about 80%. So beta is about 20% when alpha is 5%. This is a little bit of a chicken and the egg kind of thing, that, you know, because the power tends to be 80%, whenever you have people developing an experiment, they come to statisticians and they say, how big a sample size do I need for my experiment? The statisticians will usually choose a sample size to target a power of 80%. So then you tend to get more experiments that have a power of 80%. So it's, again, there's a little bit of that kind of positive feedback in that status quo, that status quo that's been set. So I'm not going to go through the details here, but one of the important things to take away from here is that if you look in New England Journal of Medicine or something, and they say, we did this experiment and we got this really cool finding, and it's statistically significant at the 5% level, that probably doesn't, or that probably ought not suggest to you that this is settled science, that this is conclusive evidence, we can move on to something else now. That probably should suggest to you that, hey, this is an interesting finding. Let's wait until, you know, 2 or 3 more papers come out to support this. And we'll see if the follow-ups find the same thing, or if there's an issue with reproducibility or replicability. There is, yeah, and you can Google this, the reproducibility crisis in the social sciences and the biological sciences, where, you know, papers are published in big important journals by very smart people, by people with all kinds of appointments and so on, and then the results can't be reproduced. And sometimes that's due to malevolence. Sometimes people intentionally mess with the data to make their result look better than it was, and that's effectively fraud. But sometimes it's just due to sampling error, right? I mean, if you do an experiment, you just might happen to get lucky. And, you know, we know that 5% of the time, when there's essentially no result there, it's going to look like there's a result. That's just statistics, right? I mean, if you wanted to prove everything to 100%, then you wouldn't know anything, and your doctors wouldn't be able to do anything, because nothing is going to be 100% certain. So if a paper can't be reproduced, that's not necessarily saying that that author was, you know, was a fraudster or something. They might have just fallen into this 5% level here. And frankly, to do them a fair service, we ought not jump to conclusions. If we jump to conclusions and say this authoritative figure said that this was certainly the case based on, you know, a p-value less than 5%, and then it gets overturned, if we adopt that mentality, then we can, you know, as kind of a reaction, go back and say, oh, that authoritative figure is a goofball and a fraudster now. Maybe that's never what they said, right? Maybe they had the proper analysis and caveats and all of that in their paper, but if we grab onto this stuff too tightly on the basis of just one experiment, we're also doing the researchers a disservice. Okay, next important topic is significance versus relevance, which I touched on in that last problem. So suppose that we have a hypothesis test that's set up as the null mu equals 100, alternative mu less than 100. Maybe we're looking at IQs of folks, and we're trying to decide if folks that have, say, a certain disease, if that impacts their IQ. So suppose as a true mean, hypothetically, like if we were omniscient, we would know that the true mean is 99.9. In other words, the alternative hypothesis is true, but only by 0.1 IQ points. We take a very large sample, 100,000 people. We get X bar observed of 99.9, as we would kind of expect from a very large sample when the true mean is 99.9. And let's say we get a sample standard deviation of 15. if we compute a p-value under the null, p is 1.75%, highly significant, p is less than 5%. So we see statistically significant evidence the true mean is less than 100. We would then reject H0 in favor of H1. We would do that correctly. This would function as expected. We would conclude that the mean is less than 100 when the mean truly is less than 100. Great, right? We have statistically significant evidence, but then the question is, do we actually care about this tiny deviation? What's the effect size? The effect size is so small that it's negligible. So do we actually care about that? Is it relevant to whatever thing that we're studying, or for whatever reason we're studying this? There's a concept in medicine called the minimally clinically important difference, and it's related to a similar idea. I was listening to a podcast from JAMA, the Journal of American Medical Association, and there was a guy, he's a clinician, he's an oncologist, a cancer doctor. So he, spends most of his day meeting with patients, developing treatment regimens, those kind of things, diagnosing what type of cancer they have, how bad it is, things like that. So most of his practice is focused on patients, but he obviously needs to keep up with the research to know what's out there. And they were interviewing him, and he said something that I actually thought I misheard him at first, but I thought it was a very important point when he clarified. He said that they said something like, how do you decide which, there's so much research out there that's coming out every week, every month. You can't read all of it. How do you decide which papers to read? He says, well, one thing I do is I go through and I look at the papers, and he's mainly talking about like experimental papers. So where they had to set up a trial and do experiments and all that. So costly things to do, not just, data mining kind of things. He says, I look through and if I see, if I see a paper with a really large sample size, I just move on. I move to the next paper. And the interviewer was a little confused too, because it sounds so absurd at first. You think large sample size, that's really good, right? And so the interviewer asked this guy, he's like, well, wait, can you clarify that? He says, yeah, because I know that the experimentalists have gone to statisticians and they've powered their study. They've asked the statisticians, they've said, every one person that I add into this experiment costs a bunch of money. I don't want to put a whole bunch of people in here if I don't need to. So they go to the statisticians and say, how big does my study need to be? How many participants do I need? Basically, how much money do I have to spend to be likely to determine whether there's statistical significance or not, to be able to distinguish between these two hypotheses. And the statistician is going to ask them, what effect size do you expect to get? Right? What do you expect X bar 1 minus X bar 2 to be based on your clinical knowledge, your research knowledge, based on your intuitive understanding of the problem? What do you think this will be? And then I can give you an idea of how big your study needs to be. They don't want to put a whole bunch of extra people in the study if they don't need to. It costs a ton of money. So if the statistician says you need to put a ton of people in your study and spend a whole bunch of money to get statistical significance, what does that say about the researcher's guess at how big this effect size is going to be? It's going to be very small. To tease out statistical significance for a very small effect size, we need a very large sample size. And that was his point. He's saying, if you needed to power the heck out of your study like this, if you needed this enormous sample size, you're really not expecting a large effect size. And as a clinician, does that meet the requirement of the minimally clinically important difference? Is it likely that this study has found something that is sufficiently different that as a clinician, he's going to change his practice, he's going to change the way he treats patients and so on the basis of that? Well, no. If they need, 5,000 people in their study to tease out that difference, it's going to be a very small difference. It's going to be a difference that's on the margins. He's not going to change his practice because of that. He'll look at another paper where they might have found something more substantial, more relevant to his practice. I thought it was just a really fun thing, because it sounds so absurd at first. He's like, oh, if I see a large sample size, I skip over that paper. But when he explained it, it's like, oh yeah, that makes actually a lot of sense from the point of a clinician who's just asking, how can I do better at treating my patients? And if I can do 0.1% better, that's really not any better. Okay, I think that says about what I want to say on that. One other detail is that typically we target alpha to be a certain, or well, not typically, all the time. We target alpha to be a certain number, and then beta is what it is, right? We set alpha to 5% and we don't even talk about beta, or we might, we might make an approximation of beta or something like that. But always setting alpha to 5%, remember, alpha is the type 1 error rate and beta is the type 2 error rate. Always setting alpha to 5% kind of says we're always setting the costs of one error versus another to be in a certain proportion. So in other words, if I choose alpha 5% and let beta be 20%, implicitly that says something about the cost. That says something about how much I want to avoid a type 1 error versus how much I want to avoid a type 2 error. And those costs aren't likely to be the same, type 1 versus type 2 error, across different studies. So there are going to be some examples where we really want to avoid a type 1 error, some where we really want to avoid a type 2 error, some where it's a little closer. So in this example, and we've been through something like this before, I've talked about this idea before, that if we want to minimize the total error, alpha plus beta, that's one approach. We can, imagine setting a cutoff, so to speak, at different points along this blood glucose number, and for lower cutoffs, we're going to call more non-diabetics diabetic. For higher cutoffs, we're going to call more diabetics non-diabetic. For a cutoff that's right at the intersection of those two curves, we're going to have the minimum total error. But that would require choosing alpha to kind of, or letting alpha in a sense float, and choosing alpha on the basis of something like this, rather than just always setting it at 5%. So maybe sometimes alpha's 3.1% and sometimes alpha 7.8%. And, if there's a good reason for that, maybe that's something that could be put into a paper, but again, these standards are usually alpha 5%. So for example, here I mentioned that, for a jury trial, the cost of making a type 1 error of sending an innocent person to jail is typically viewed by our society as much higher than the cost of letting a guilty person go free. For a TSA screening for something like whether somebody's carrying a weapon onto the plane or in the airport, the cost of a false positive, in other words, saying we think this person has a weapon when they actually don't, is probably pretty low, right? You go through the hands up thingy and they say, oh, there's something suspicious in your pocket, and can you take whatever it is out, and you pull out your ticket or something that you forgot to take out of your pocket, and they're like, oh, okay, that's fine, right? So what was the cost of that false positive? Pretty low. They just say, oh, this is suspicious, can you clarify? You clarify, all right, no big deal. Or maybe at worst, you have to let them open up your suitcase and look through it, and they rummage around, and that's the end of it. But the cost of letting, say, a bomb onto a plane is obviously significantly higher. So it's not always clear that type 1 error should be pushed down at the expense of type 2 error, or vice versa. For medical tests, there are costs on both sides. If you tell a person who doesn't have a disease that they do have it, maybe they undergo, painful or expensive treatments that they didn't need to undergo. At the very least, it's going to be stressful and worrying for them. But if you tell them that they don't have a disease when they do have it, the disease is likely to progress and get worse, and maybe become harder to treat, or have worse morbidity and mortality. And then probably the biggest issue here, maybe I shouldn't say biggest, but most widely recognized and most widely complained about, maybe, by people in the stats world, is the misinterpretation of p-values. That what the heck does a p-value mean? The ASA, the American Statistical Association, actually released a publication that was like a statement on p-values or something, trying as hard as they can, screaming from the rooftops, this is what these things actually mean. Please stop misinterpreting these. So we might be tempted to say something like, okay, what's a p-value? Well, a p-value is the probability of getting such evidence given that the null is true. We might say something like, okay, well, if the p-value is small, then that means that it's unlikely the null is true. In other words, we might say because the p-value is small, the probability that the null is true in light of this evidence is also small. At first glance, that seems like a pretty reasonable thing to say. In fact, I mean, if you said this to anybody who hasn't taken a stats course recently, if you said, is this true? They'd probably say yes. If the likelihood of getting evidence under a certain hypothesis is small, then the likelihood of that hypothesis being true, given the evidence, is also small. The problem is we can clearly see this is not correct. Well, it's not always correct, right? Sometimes it may be correct, but other times it may not be. This is a Bayesian statement. We're flipping the condition. We can't just say because one of them is small, the other one is small. We need to apply Bayes' theorem to flip that condition like that. We can't just make this statement. So in other words, in a jury trial, this is sometimes called the prosecutor's fallacy. In a jury trial, we might be tempted to say something like, well, there's all this circumstantial evidence that links this person to the crime. The person who robbed the bank was the same height as this person. They had the same hair color. They got in the same make, model, and color of car that this person owns. All of the circumstantial evidence, right? It's very unlikely for all of this to exist if this person was, say, just someone randomly chosen from the population, rather than if they were the one who committed the crime. So the p-value is small. Therefore, it's unlikely the person's innocent and you should convict them. That is not a correct statement to make. That's just putting into words what is put into conditional probabilities up here. So let's work through an example on this, because I think this is an important thing to talk about it in some detail. So suppose we have two competing hypotheses as, let's say, the jury. The person is innocent of bank robbery and the person is guilty of bank robbery. And let's not worry too much about the, let's suppose that things are well enough defined that we can determine whether somebody's innocent or guilty if we had all the information and all of that. Suppose there's a plethora of circumstantial evidence, and we estimate that the probability of evidence, of such strong evidence existing, given the person we're innocent, is 0.5%. We look at this and we say, oh, this is highly significant. This is statistically significant, even at the 1% level. And so we reject the hypothesis of innocence, and we instead move forward with guilt, with hypothesis of guilty. So we call the person guilty and we convict them. Is that consistent with what we actually think that we're doing? Probably not. Probably what we mean when we say we think the person's guilty is not we were able to, as frequentists, reject the null in favor of the alternative. We probably mean something more like, I think it's very likely the person is guilty and very unlikely the person is innocent. But that's really a Bayesian statement, isn't it? If I'm starting to talk about the probability that one hypothesis versus the other is correct, that's fundamentally Bayesian. The frequentist would say, well, mu is fixed. One hypothesis is correct, the other is incorrect. We just don't know which one. If we're starting to talk about probability of H naught versus probability of H1 being true, we're talking like Bayesians. We can't use hypothesis tests to make conclusions that are fundamentally Bayesian. So really what we think we're saying is the probability the person is innocent given the evidence is less than some small number. But really what we're basing that analysis on is that the probability of evidence given innocent is less than some small number. This is a very nuanced difference, but a very important difference. So why aren't these the same? Well, let's take an example. Right? Most people don't rob banks. The prior probability that somebody randomly chosen from the population has robbed the bank is very, very small. So with no other evidence, we consider it very unlikely this guy is a bank robber. So before the trial, let's say that our probability distribution, our prior distribution, is probability of guilty 0.01%, probability of innocent 99.99%. These are numbers that are roughly taken off of the FBI's crime statistics. And this is even, like probability of guilty would even be a little bit smaller than this, but I just rounded it to 0.01%. So now what's the probability of guilty given evidence? Now, before we move forward, you might balk at this and you might say, wait, well, you're pretending that this guy who's on trial, who's at the defendant's table, was just some random guy plucked off the street and stuck there. Well, doesn't that ignore the fact that, he was arrested by the police, presumably based on probable cause? He was charged by the DA, again, presumably based on probable cause. The lawyers went to the judge and gave their arguments for, why the case should be dismissed. And the prosecutor said, no, the case shouldn't be dismissed because we have this evidence. And the judge concluded that the case can go forward to trial. Shouldn't we include all of that? My argument would be no. And this is why. If we consider a piece of evidence, let's say that the hair color of the defendant matches the hair color seen on the robber. Well, the police probably used that piece of evidence to arrest them. The DA probably also used that piece of evidence to charge them. The judge probably also considered that piece of evidence to let the trial move forward, right? Same with all the other pieces of evidence. And then that evidence is presumably going to be put forward at trial as well. If we look at this person as somebody who's 75% likely of committing bank robbery because of all this stuff that happened before, we're double or triple or quadruple counting all the evidence before we even get to the trial where it's going to be counted again. So we probably ought to, at the outset of the trial, presume that all of the evidence is going to be presented at the trial. The trial is going to be the mechanism through which the facts are found. And this evidence that's presented at trial should be weighed against a defendant that's presumed innocent, right? Or against a defendant that effectively is, we say, this is a random person plucked from the population, stuck in the defendant's seat, and then the evidence starts to weigh against them. We can't count all of that previous stuff because then we're double, triple, quadruple counting all of the evidence, and clearly that's not a reasonable thing to do. So even though this might seem counterintuitive, I think I've hopefully made an argument in favor of approaching the problem this way. So then what's the probability of innocent versus probability of innocent given evidence? Well, we can go through some calculations here. This was our p-value of 0.5%, probability of evidence given innocent. That's the p-value, 0.005. We have our prior probabilities here. And then we'll also presume that given the person's guilty, all the evidence will line up with them. So if this actually is the guilty person that's sitting in the defendant's seat, they're going to have the same hair color as the bank robber and so on. We'll make that assumption. That might not be strictly a true assumption. Maybe they dyed their hair or something to rob the bank. I don't know. But we'll kind of presume that that's true. And after all of this, keep in mind, this is probability of innocent given evidence. Probability of innocent is 98%. So their probability of guilt is about 2%. In other words, we should be saying we're about 2% certain that they're guilty. But we might be tempted to say something like, we think there's only 0.5% chance they're innocent, or 99.5% they're guilty, if we misinterpreted that p-value. Right? So then we might ask, okay, well, I mean, certainly at some point, the circumstantial evidence has to add up to a point where you can say, with some sort of probabilistic certainty that the person is guilty. So the Bayesian kind of equivalent in a loose sense of a p-value less than 1% might be something like probability of innocent given evidence being less than 1%, this posterior probability of innocence being less than 1%. How compelling does the circumstantial evidence have to be? How small does probability of evidence given innocent have to be? How small does the p-value have to be for the Bayesian to agree with the frequentist and put the person in jail? And the answer is roughly 1 in a million. Not 1 in 100 or 1 in 200, which would satisfy the frequentist, which would drop the p-value below 1% and be highly significant. But the Bayesian would require circumstantial evidence of 1 in a million, right? Basically saying in the greater Pittsburgh area, you need to show me enough evidence that like this is the only person in Pittsburgh that meets all of these, these criteria, certain height, certain hair color, certain car, whatever it may be. That's a big difference, right? The frequentist would say, 1 in 100, 1 in 200. The Bayesian would say 1 in a million to declare guilt. So we don't want to fall into this trap of misinterpreting p-values and thinking that low p-value means that it's unlikely the null is true. And as an aside, there have been quite a few people convicted and had their convictions overturned after years of hassle and being in jail and so on the basis of what I would call fraudulent statisticians, people presenting themselves as statisticians who are experts in the field and who just made errors that I would say were silly errors if it didn't result in such suffering for somebody. But I mean, what we would call silly errors, things like assuming independence when they really ought not have, things like that. Things that a first semester stats student knows to look out for. So it's, these cases do pop up. And I always say that if you're ever a prosecutor and you have me on or as a potential juror, just strike me right away, because like it would be very difficult to convince me that somebody is guilty for most crimes, because most prosecutors, maybe I shouldn't say most prosecutors, but issues like this are very, very common. So to actually prove beyond a reasonable doubt that something is true is extremely difficult, even in science, even in something as controlled as a scientific experiment. So this is kind of like a joke to lighten the mood a little bit, from XKCD, the comics folks who make funny comics. So this is titled, "Did the sun just explode? It's night, so we're not sure." So person on the left says, "This neutrino detector measures whether the sun has gone nova." Person on the right says, "Then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells us the truth." So they try it, they push the button, and the frequentist they push the button and the machine says yes. In other words, the machine claims the sun has exploded. And the frequentist says, well, the probability of this happening by chance is 1 in 36. In other words, the probability that the sun hasn't exploded, that it rolled the 2 dice, and that it said lie to us, in other words, that it generated a false positive. And 136 is 0.027. Since that's less than 0.05, my p-value is less than 0.05, the frequentist concludes that the sun has exploded. And the Bayesian says, "I'll bet you $50 it hasn't." So, right, this frequentist statistics completely leaves out the idea of a prior probability, the idea that we have an awful lot of experience with our world, and we probably ought not just forget about all of that experience. And as an aside, it's always a good bet to bet somebody that the sun has not exploded. If you lose the bet, you're not going to do anything with that money in 8 minutes anyway. So, and then last couple of details, these aren't so important, but these are things to consider. So consider this narrative. Suppose that I told you I ran a study, I gave my medication to test subjects who were very ill, and 50 of them recovered within 24 hours. The typical recovery time for this type of illness is 1 week. Does this represent strong evidence for the efficacy of my drug, that my drug makes people get better more quickly? And you might look at this and there's a very natural question to ask. Well, 50 of how many? Was it 50 of 50, or was it like 50 of 10,000? Right? If it was 50 of 50, then yeah, this pretty obviously represents strong evidence. If it were 50 of 1,000, well, who knows? Maybe that could have just happened by chance. Some people might just get better more quickly. So the moral of the story is that the number of positives only tells half the story. The number of negatives as at least, or probably more important than the number of positives. And as an aside, I have a friend who's an actuary, and during COVID, he was posting the COVID, positive test result numbers occasionally, and And basically he was falling into this error of doing exactly this. This is somebody who's very good at statistics, who, understands the book side of statistics very well to be an actuary, and is, in the insurance side of things, very good at the application and interpretation of statistics. But this was just an oversight of his. He was publishing these positives and making statements on the basis of the positive tests, but not considering the negatives. And so I kind of pointed this out to him, and so it's something that can slip past, even very well trained, very smart people who, normally wouldn't make this kind of error. It's an insidious error. So if I tried to publish a paper in JAMA and I said, 50 of my people got better very quickly, they would always ask, well, out of how many, right? Like that's very important. But what if we zoom out a level and I say there are 3 published papers in good medical journals that have all concluded, the 3 of 3 have concluded that this thing is true, that they got statistical significance for whatever this statement, that, this drug works or this treatment regimen works better or whatever. And a lot of people would just say, oh, 3 of 3, like, that's great. Like that's conclusive evidence. I can just accept that as essentially truth and move forward. But we never said how many people tried to prove that thing and failed, right? How many research groups out there have set up an experiment to try to prove that, say, this way of treating this condition works better and failed? Are these 3 groups the only ones that tried it and they all succeeded in showing that this treatment regimen is better? That's very convincing evidence. Is this a hot area with a lot of grant funding and 20 groups have tried, or 50 groups have tried, or 100 groups have tried, and 3 of them have shown that it was better? With a p-value of 5%, if 100 groups tried and 3 showed that it was better, that's certainly likely to have happened by chance. Even if 20 or 50 groups have tried and only 3 showed that it was better, that's much less convincing. So how do we know how many groups have tried to show something and failed versus how many tried to show it and succeeded? And the answer is because of a publication bias. That's not an easy thing to know. People tend to not want to publicize whenever when they take a bunch of grant money, spend a bunch of money doing some experiment, and it basically fails, basically doesn't show what they thought that it was going to show or what they wanted it to show. And also, big publishing houses don't want to publish papers that are like, hey, we tried to show this thing and didn't show it. They want to publish the groundbreaking research, the thing that's going to be, the next development in cancer or something like that. So there's a publication bias on both sides, that negative results are much, much less likely to be published than positive ones. A few journals here and there have tried to do something where they say, basically, you have to register your study with the journal before you do the study if you want to be eligible to publish your study in that journal after you do the study. So that gives you an idea of what the negatives versus positives ratio is. But unfortunately, as far as I know, the big name journals haven't done that. So this publication bias is really something to think about. And again, this probably factors into the issue of the replication or reproducibility crisis, where so many results that are kind of taken as known and as solid science aren't able to be reproduced later on. So if we have 3 out of 3 papers that said something and there were 50 folks who tried and that happened by chance, if somebody tries to produce it later on to confirm it, or to reproduce it later on to confirm it, what are the chances they're going to succeed? Maybe 3 out of 50 or something. If that would be what we'd expect, 6% chance, like probably not very likely. So, and then lastly is just kind of a complaint about, I suppose, the awkward setup of hypothesis tests. It's an argument by contradiction, essentially. We want to show that something is true. So we start by assuming the opposite of what we want to show. And then we gather data. We say, how strange would the data be if the opposite of what we're trying to show is true was actually true? And then if that would be very unlikely, and it would be more likely under our assumption or our worldview, then we reject the thing that's the opposite of what we want in favor of the thing that we want. It's a very backwards way of approaching this, right? What we would like to say is, I think my worldview is true, and there's a competing worldview. Let's get numbers that say, what's the likelihood my worldview is true versus the competing worldview? That's what we would really like to do, but that's really a Bayesian approach. So this frequentist approach forces us into this kind of backwards, kind of backdoor approach. So after all of this complaining, why do we use hypothesis tests? Why do we use frequentist analysis? There are good reasons. I don't want you to think that this is a garbage thing or that there's no good to any of this or whatever. This is good statistics, provided that people are aware of the shortcomings. There are going to be shortcomings and caveats for any method that you use, including Bayesian analysis. As much as I like Bayesian analysis, there are shortcomings and problems there as well. So there aren't a whole lot of options available to make such decisions. There's hypothesis testing, Bayesianism, a couple of other outlooks. Bayesian analysis, well, we have to decide on a prior distribution, right? We had to decide this person at the defendant's table, what's their prior probability of being guilty of, say, bank robbery? Should I use the FBI statistics? Well, those are only really people that were convicted of bank robbery. Is that a good prior to use? Should I use only people that are in Pittsburgh or greater Pittsburgh area or Pennsylvania, or right? What should my population be? So how do I choose a prior? It's not a trivial decision to make. Or even worse, I could, in theory, I could intentionally choose a prior to help me get the result that I want to get out of the other side. So if I was a researcher, I might choose a prior knowing that that's going to make it easier for me to get statistical significance or whatever the equivalent would be, and kind of publish my paper on the back end. Is somebody likely to do that? Well, when you put somebody's job on the line, if they, the publish or perish mentality, that makes it really tough to not do that. And the status quo is frequentist analysis. Some studies are showing that Bayesian methods give better results, but still, if we have 50 or 70 years of built up data and evidence and scientific research based on doing this a certain way, and we just suddenly flip to Bayesianism, it makes it very hard to compare across that divide. At least, maybe not very hard these days. We have lots of computers and stuff that help out, but it makes it more difficult. I can't just look at 3 experiments done over 20 years and just compare the results one to the other directly. And then the other thing that I want to point out is, I'll skip over the math here, but basically along the bottom, we have the probability that H naught is false from a Bayesian perspective, the prior probability that it's false. And then from a Bayesian perspective on the y-axis, we have the prior probability that H naught is false, given that a frequentist would have rejected it, given that a hypothesis test generated a rejection. Under some certain assumptions, we assume power is 80%, beta is 20%, and so on. And the prior probability H naught is true is pi. That's not 3.14. That's just another letter p, because we have too many p's floating around already, right? We've used p for the p-value already, so this is just a different p. But we notice that, okay, if I have, well, probability of H naught false, if that was very low, like our bank robber, right? If a probability a person pulled off the street is not innocent, but guilty of bank robbery, if that's very low, if I'm on the left side of the graph over here, I see that it's very unlikely that it's false, given that the frequentist rejected it. In other words, there's a large amount of discord between the Bayesian approach and the frequentist approach when we're on the left side over here. When we have a null that we're very confident is true, the Bayesian and the frequentist are going to come up with two very different conclusions. But let's say that I'm in the middle here at 50%. In other words, where the Bayesian says for the prior distribution, it's as likely that the null is true as it is that the alternative is true. Then you tell the Bayesian that the frequentist did their calculations and generated a rejection. Now, what is the Bayesian's perspective on that new piece of information? Now the Bayesian would say that they are 95% confident, 94% confident that H naught is false. So here, the frequentist says that the p-value is less than 5%, and the Bayesian says that essentially the probability that H naught is true is about 5%. There's much more concordance between the two. So if we kind of stay away from this edge case where it's very likely that or very unlikely that H naught is false, or very likely that the null is true from the Bayesian perspective, if we stay away from that edge case, if we stay away from, like, trying to argue that the world is flat when the null is that the world is round, although I don't want to get into political discussion here, but if we stay away from things like that, then there actually is a lot of concordance between what might be considered a Bayesian approach versus this hypothesis testing approach. It's really whenever we're trying to overturn, strongly weighted evidence. And unfortunately, those are the results that get the most press and the most interest, right? Is, oh, you really thought that this was right, but I've shown that it's wrong. Those are the ones that get the most interest, the most publication, the most media attention, and those kind of things, and probably the most tenured positions, right? And those are also the ones that fall on this left side over here, where that rejection maybe isn't as strong in those scenarios as it might be in other scenarios. And so some practical takeaways.